Alright, so we have a question under specific heat capacity. Okay, so this is gonna be thermodynamics, thermochemistry. Okay, so find the minimum amount of ice at negative 10 degrees Celsius needed to bring the temperature of water that is initially at 20 to 0 degrees Celsius. So there are only two things we have. We have ice that is initially at negative 10 degrees Celsius, and then we also have water that is initially at 20 degrees Celsius. So first to understand this, we have, let's say we have a container that is having water. This is a scenario. So what happens if you get to add ice? So if you add ice to this water that we have, what's going to be happening is water at 20 degrees Celsius has got heat, has got more heat, and then the ice is cool. Okay, so the water is going to be losing heat. So the water will be losing it to what? To ice. So not until they get to be the same state and same temperature. Okay, I hope you get that. So if you have water, water is going to be losing its heat to the ice, to melt the ice. Okay, first of all to cool down the ice, and then also get to melt it until they get to the same temperature. Okay, so if we look at the question is asking us to determine how much of ice will be required to make the water at 20 degrees Celsius lose its heat, not until it gets to 0 degrees Celsius. That's what the question is asking us. So if the water is going to get to 0 degrees Celsius, it means that ice is also supposed to end up as water, because the final result is just going to be water at 0 degrees Celsius. So for that to be attained, let's understand what's going to happen. So for that to be attained, actually, let me explain. I'm sure you've come across the heating curve. So what happens is, if you have a solid state, first of all, okay, what happens if you begin to increase the temperature? You increase the temperature, increase the temperature. So you're still cooling, increasing the temperature of a solid. Now, when it reaches this change of state to be constant for a specific period of time, and then again, it was converted to liquid, and then the liquid again, constant, and then gas. So why am I bringing this into picture? So on this side, you've got the temperature. Let me say this is 0 degrees Celsius. That's 100 degrees Celsius. So we understand that at this point, what you have is a solid. At that point, what you have is liquid. At that point, what you have is a gas. So here is this part. This part, the temperature is constant because we have conversion of what? Of states at the same temperature. Okay, so in this case we're going to have ice, so we have to cool first of all the ice from negative 10 all the way up to 0. After we've cooled it, we also have to now use some energy to convert it from solid form to the liquid form. That's in terms of the ice. Now in terms of water, we're just going to cool it from 20 to 0 degrees Celsius, no change of state. I just needed to put this diagram so that you can understand something. So therefore, the amount of energy that is going to be gained by the ice for it to be cooled. So first of all, we have ice. Remember I said the ice is initially at negative 10. So we're going to increase to 0 degrees Celsius. So first, to determine the amount of energy required to increase the temperature to that, we use MCAT. So Q is equal to the mass, and then of course the specific heat capacity delta T. Okay, the other formula that we're going to be using here is Q is equal to the latent heat, okay, of fusion multiplied by the mass. So I can just say ml. Now this is the amount of energy that deals with the conversion of state. So here you use the mass, and then there you use the latent of fusion in this case. Okay, there's also latent heat of vaporization, amount of energy required per mass in terms of changing the state to vapor. In this case, it's from the solid to the liquid form. So let's first of all determine the amount of energy that's required to heat up the ice to 0 degrees Celsius. Okay, because negative 10 is very cold, and then we're trying to increase the temperature by making it a bit warm. whatever. So let's say Q is equal to the mass for the ice is what we're trying to find, so just put M. The specific capacity of ice, where is the specific capacity of ice? We are told it's that. So that is 2.09. Okay. And then the change in temperature is from negative 10 to 0, so it's 0 minus negative 10. So after we've multiplied all that, the Q1 is going to be end up as 2.09, so M and then 2.09 multiplied by positive 10, which if we multiply 10 times 2.09 will be 20.9 M. Okay. Now, this ice is also supposed to be converted to water, because we are told at the end of it all we need to have water at 0 degrees Celsius. So the ice is obviously supposed to become water, right? So we have a conversion of a state now. Conversion of a state, we're going to use ml, the mass multiplied by the latent heat of fusion. In this case, that's 355. So Q2 is just 355 M. So we have to be careful. All these are using kilograms. Kilograms. Only the water was given in terms of grams. Now, on the other hand, water on the other hand is supposed to be cooled down from 20 to 0. So that means it will be losing it, right? So I'll put a negative in the formula to be losing it. So negative. So we use the same change in temperature, use this formula. Change in state, use that formula. So water wasn't changing state, we're just cooling it. So move the mass there was 100 grams, divide by 1000, that will be 0.1 kilograms. And then the specific capacity of water was given to be 4.185, that is in kilograms, and that is in kilojoules. And then change in temperature, that will be 0 minus 20. So therefore, if we look at what we have, perform our calculations, what are we going to get? So we're going to have 0.1 multiplied by 4.185 and then multiplied by 20. So that would be a positive 8.37. Okay, now that would be in kilojoules. Very important, kilojoules. So one thing that you need to understand is this is the amount of energy that is required to cool down from 20 to 0 degrees Celsius. Now that very amount of energy required to cool down, or this is the amount of energy that is supposed to be lost. So this amount of energy that's supposed to be lost by the water for it to cool down is the amount of energy that will be required to basically cool down the ice and also convert its state. Now we need to determine the amount of ice that can require that much of energy. So that's the value of the mass now. So in short, what we're trying to say is the amount of energy required by the ice to reduce its temperature from negative 10 to 0 plus the amount of energy required by the ice for it to change state should be equal to the amount of energy that is going to be lost. Lost by what? Going to be lost by the water for it to actually reduce temperature. Okay. So looking at what we are using, we're using kilojoules. So it means our mass in these terms is we're going to end up finding it in terms of kilograms. So therefore, if we add 20.9 plus 335, that becomes 355.9 M is equal to 8.37. So let me actually take the kilojoules to joules so that we can end up with grams in answer. So that means we can just multiply by 10 to the power 3, and then our m becomes, so 8.37 multiplied by 1000 divided by 355.9. So the mass is 23.5 grams of ice. That's the amount of energy that will be required. This is the amount of ice that will be required to gain the energy that is going to be obviously lost by the water that is cooling. Okay. So I hope you've gotten the basic idea on conversions of state and everything, but this is a very simple question. Just requires you to have the conceptual understanding of what happens as you reduce the temperature, and then as well as you increase the temperature, and then as well as you change the state.